In this video, we solve problem 10.2.19-T from Essentials of Statistics, 6th edition by Mario Triola. The problem statement says, find the regression equation, letting the first variable be the predictor, X variable. Using the listed lemon/crash data, where lemon imports are in metric tons and fatality rates are per 100,000 people, find the best predicted crash fatality rate for a year in which there are 475 metric tons of lemon imports. The question says, is the prediction worthwhile? So we have 5 ordered pairs of data there, and we're asked to find the equation of the regression line. There are actually 3 different ways that we can do that. We have 2 sets of equations that will allow us to compute all of this by hand. And then we also have technology that will just give us this regression line if we give them the input of our X values and our paired Y values. So I'm going to show you how to find this regression line in 3 different ways. Notice that we are asked to round the constant term to 3 decimal places in the problem statement. And we're also asked to round the coefficient, that's the coefficient of X, to 6 decimal places as needed. So in this video, I'm going to take you through all 3 methods for finding this regression equation. The first method is the method that I would use if I were doing all of this by hand. So our B sub 1 and B sub 0 are given by these formulas, which means that I need the sample size, which is 5, because we've got 5 ordered pairs. Then we need a sum of the x's times y's. We need the sum of the x's and the sum of the y's, and we need the sum of the x's squared. And then down here, we see that we need sum of the y's, which we already have, sum of the x's squared, which we already have. There's nothing new here. So all of the expressions that we use up here, we can use down here to find our y-intercept. So I guess what we need next is a column here with the x's times the y values. So, oops, sorry about that. I am literally going to multiply this with this. That's what goes in this entry right here. So this is 227 times 16.1. Which happens to be 3,654.7. And there's not quite enough room, but we want to do that for all of these rows. So we'll do 261 times 15.8. And we get 4,023.8, 4,123.8. Then 354 times 15.5. Then 463 times 15.5. And then 542 times 15.1. You get the idea. Probably don't need to watch me type things into my calculator to get this idea, but we're just multiplying those 2 together and then we're writing our values right here. Now over here in the x squared column, we're just going to take each of our x values and square them. I actually might just leave that as it is. I don't need to know what each of those individual x values squared is. I just need to know what the sum of those is. So in order to get ready to use these formulas, I will take each of these columns and add all the values in the columns now. If I'm adding up all of my x values, this is what I get. I've got 227 plus 261 plus 354 plus 463 plus 542. So the sum of the x's is 1,847. The sum of the y's is 16.1 plus 15.8 plus 15.5 plus 15.5 plus 15.1. So that's 78. The sum of the x's times y's is this 3654.7, and you just keep going. You just add, and I get 28,207.7 if I've done all of that correctly. And then here, I don't even have my x's squared, but I will just take each value of x, square them, and then I'll add them together. And sometimes we make calculator entry errors, so it's really helpful to use technology to do something like this. So I get 753,099 for the sum of the x's squared. So before we go any further, I think I want to use Excel to compute these values and see if we get the same sums down here. So let's use Excel just to confirm before we substitute into the formulas for B sub 1 and B sub 0. So I've created a spreadsheet. In this column, I want the x's times y's. So I type equals, I select the x value, and I select the y value, and I hit enter. Then I'll just drag and drop. See how nice that is? Then over in the x squared column, I type equals, I select the x value, and then put a caret and then a 2 there. And then we'll drag and drop there as well. And then for each of these, I want the sum. So I'll take the sum, or don't forget to type your equals sign, otherwise it won't calculate for you. So you want equals sum, open parentheses of, select those cells, close parentheses, and then drag and drop. So the sum of the x's is 1,847. That's exactly what I have on my paper. Sum of the y's is 78, great. Ooh, it looks like I made a mistake with the sum of the x times y's on my paper over here. The sum of the x's squared is correct. So maybe I entered this incorrectly here. I've got 3,654.7. That's right, that's right, that's right, that's right. Oops, this one's not right. I must have entered that into my calculator incorrectly. So this value right here is wrong on my paper. So you can see how easy it is to make a little mistake like that. That's why it's always good to use technology or confirm with a friend while you're both doing the same calculations. Okay, so I know now just from looking at this that the sum of the x's times y's is supposed to be 28,626.2. And I know that this value right here is questionable. So let me do that again. I have 463 times 15.5. Yep, that was supposed to be 7,176.5. And if I correct that, now I bet everything adds up to be what it's supposed to be. So we have 28,626.2. So that's right. Okay. Now that we have these four values, we can use them in our formulas for B sub 1 and B sub 0. So for B sub 1, I have a 5 times the sum of the x's times y's. So that's 28,626.2. Then I want to subtract the sum of the x's, which is that 1847, times the sum of the y's, which is 78. And then I want to divide all of that by 5 times the sum of the x's squared, which is that 753,099, minus the sum of the x's, which is 1847 squared. And I didn't quite leave myself enough room over there, so I'm going to continue my work down here. And I'll do the numerator first here. So I have 5 times 28,626.2 minus 1847 times 78. So the numerator is negative 935. And let's see what the denominator is. It's 5 times 753,099 minus 1847 squared. And so that's 354,000. 86, and then we'll just take those two numbers and divide them. So I'll take negative 935 divided by the last answer, and I'll get a decimal approximation. Now I get negative 2.6406 times 10 to the negative 3. Now remember what the fine print said. It said round the coefficient to 6 decimal places. And b sub 1 is the coefficient, they're referring to the coefficient of x here. So they want us to round this to 6 decimal places, and I can see why. This decimal is very small. So this is going to be negative 0. Since that's 10 to the negative 3, 0.00264, and that would be to 5 decimal places, and then I have a 0.6. So if I'm rounding up to the 6th decimal place, I'll have a 1 there, and that's an approximation. Okay, so that is how we get b sub 1. We can use this formula to get b sub 0. Now notice that b sub 0 has exactly the same denominator as b sub 1 does. So we're still going to have 354,086 in this denominator, but in the numerator we'll have the sum of the y's, which is 78, times the sum of the x's squared, which is that 753,099. And then we're subtracting the sum of the x's, which is that 1847, times the sum of the x's times y's, which I didn't quite leave myself enough room there. That is 28,626.2. So that's my numerator there. So let's do that over here. B sub 0 is this, 78 times 753,099 minus 1847 times 28,626.2. And we get this numerator, 5869130.6. Whoa, so 5,869,130.6. And we're taking all of that and dividing by 354,086. And we're asked to round the constant term to 3 decimal places. So I have 16.575 here. So putting these two pieces together with the equation of the regression line, y hat, that's our predicted value of y using the regression line, is equal to the constant term, which is approximately 16.575, plus the coefficient, which is negative 0.002641 times x. So let's type this into my lab statistics and see if it likes this answer. Now I also want to show you that you can get the same answer using the other formulas as well. So this is just our first attempt. And then I want to show you how you can get the same answer using Excel, which is very fast, using the second set of formulas, or just using Excel's regression capabilities. Okay, so my constant term, or my y-intercept, is 16.575, and the coefficient of x is negative 0.002641. Great, it likes that answer. Now, I know we can move on from here, but I would like to show you how to find the regression equation using the other two formulas as well. So I'll share my paper with you to do that. So the second set of formulas for b sub 1 and b sub 0 is based on the linear correlation coefficient R and those two standard deviations. This is the standard deviation, or the sample standard deviation for the y values, and this is the sample standard deviation for the x values. So we can find those and find the mean y value and the mean x value and use these formulas to find b sub 1 and b sub 0 instead. Now these require more computation. Even though these formulas tend to look more intimidating, with these, all we have to do is create a column of x times y, create a column of x squared, and add. We can do that with all of the raw data that we have. This implies a lot more computation. R has a formula like this that would be that we would have to use in order to find R by hand. And to create or to find each of these sample standard deviations, we would have to find the mean x value, the mean y value, subtract those from each of the x values and y values, square those, divide by the sample size minus 1 for each of those. So there's a lot of computation that goes into computing these three numbers. But once we have those three numbers, we could find b sub 1. And if we already have b sub 1 in the two sample means, we could use this formula to find b sub 0. So rather than doing all of this by hand, I want to show you in Excel how we can do this. Excel can easily compute a sample standard deviation and the Pearson linear correlation coefficient R. It can also easily compute these mean values of X and Y. So I want to show you that we're going to get exactly the same answers as we obtained using these formulas, using these formulas. So let's do that in Excel now. Okay, so using the original formulas, the numerator for b sub 1 was the sample size, which was 5, times the sum of the x's times y's, minus the sum of the x's times the sum of the y's. And the denominator was the sample size times the sum of the x's squared minus the sum of the x's squared. And so when I take the ratio of those, I get that value, which is the same value that I got when I did all of those calculations by hand. Now the numerator for b sub 0 is different. The numerator for b sub 0 was the sum of the y's times the sum of the x's squared minus the sum of the x's times the sum of the x's times y's. And we take that numerator and divide by the same denominator from before to get b sub 0. So we get those two values using Excel to do the calculations. I highly recommend that you use Excel to do calculations like this. It's good to do it by hand just so that you remember what Excel is doing. But if you can write the little bit of code that tells Excel what to do, then for me, that indicates that you really understand the process. We can easily make typing errors or transcription errors. So using technology for these purposes is great. But we could compute B1 and B sub 0, or B sub 1 and B sub 0 using these formulas as well. That requires finding the two sample standard deviations, the Pearson correlation coefficient R, and then the B sub 0 using those sample means. So to do that, I'm going to create a row here of sample standard deviations. Those can be calculated in Excel using stdev.s. S for sample standard deviation, open parentheses, drag and drop, make sure you highlight all of those. So you have to type equals stdev.s, open parentheses, and then you select your x values. And I'll drag and drop this way so that I calculate the sample standard deviation for the y values as well. Now for the Pearson correlation coefficient R, I could use these totals from these columns to find R, but it's much easier to just use Excel's built-in Pearson function. So for that, they want us to open parentheses and then select the first array. That's the array of X values, then type a comma, and then they want the second array. That's the array of Y values, and close parentheses and hit enter. That's your R value. Then B sub 1, that is our slope, that's the number that's multiplying X, is R times the ratio of those sample standard deviations. So it's the sample standard deviation for Y divided by the sample standard deviation for X. And see, we have here the same value that we have over here, so that's great. Now to find B sub 0, we need sample means. So I will use Excel's average function. So you need to type equals average, open parentheses, select the X values, close parentheses, drag and drop. So I've got the average X value, the average Y value, and B sub 0 is the average Y value minus B sub 1, which we just calculated, times the average X value. Notice that we get the same thing there. Now, typically, these formulas Now, typically these formulas are used together and then these formulas are used together, but you could just as easily use this formula to get your B sub 1 and then find the two sample means and use this formula to get B sub 0. So some people like to do this and this rather than doing this and this, just because this is cleaner and it takes up less space and it's sort of easier to think about than all of this. This is not difficult to do. It's just a lot of numbers and a lot of expressions, and there might be a lot of potential to make mistakes just due to reading it incorrectly or writing something down wrong. Whereas this, I think we can see that if you just take this equation and rearrange it, we have y bar equals b sub 0 plus b sub 1 times x bar. Well, that's just like this, but with the mean value of y and the mean value of x substituted there. So that's just a rearrangement of the formula, which makes that really easy to remember. But now you'll never have to remember any of these formulas. All of these are on the Triola formulas and tables sheet that you can refer to. So using these formulas, we can find B sub 1 and B sub 0. We get the same answer as we saw. We can also use Excel. So let me show you how to use Excel to get the same answers, just using Excel's built-in regression capabilities. So what I would do if I want to find the regression line is I would highlight the cells, the X's and the Y's, and then go to this scatter plot. Select that right there. And now I've got a scatter plot and I want to add a regression line to it. So I go over here to Trendline and then choose linear. Now if I select this and I go to Format Trendline, it gives me some options over here on the right. So it says display equation on chart. I'll choose that option. And then you can see that we have our regression line over here. Now they only rounded the coefficient of x to 4 decimal places. So that might be a problem if you are using this to come up with your regression line, especially if MyLab Statistics is asking you to round to 6 decimal places. In that case, we might have to use the formulas. I think it's probably also possible to set up this trend line. Oops, I guess let's select that again. Format trend line. It's probably also possible to format this so that when it displays the equation, it gives you some options for the number of decimal places, but for some reason I'm not seeing that option on Excel on my computer right now. So that's not good. I'm not really sure how to do that, but I guess we could Google it and figure that out if we wanted to. So we see we get the exact same answer. They're just rounding a little differently. So we couldn't use this rounded version to get the correct answer in Excel, but we can use the original formulas, which were made for hand computation. We can use the formulas in terms of the sample standard deviations and the sample means and the linear correlation coefficient R, or we can use technologies, built-in linear regression capabilities to find the equation of the regression line. Any one of those would be fine. Okay, so let's go back to our homework assignment and see what else they're asking us. Now the next question says the best predicted crash fatality rate for a year in which there are 475 metric tons of lemon imports is blank fatalities per 100,000 in the population. Now remember how this works. You can use this regression line to predict the crash fatality rate given a number of lemon imports if there is evidence of a correlation between those two variables. Now, there may not actually be evidence of a correlation between those two variables, so we need to check that out first. That requires looking at our R value. So let's go back to Excel and look at our R value and then think about whether we have evidence of a linear correlation. Okay, so we computed our R value already. It's right here. it's not really the right color. Maybe I'll just pick a different color. So that is very close to -1. So it would seem that there is probably evidence of a linear correlation, but we should probably check that R value by comparing it to our critical values for R. So in order to determine the best predicted value of Y, we need to see if there's evidence of a linear correlation first. So we'll compare the R value that we have to the critical values of R in our table. I believe it's table A6 from the handout that goes with our textbook. Okay, so we're here looking at our formulas and tables from Mr. Triola. If we want the critical values of R for alpha equals 0.05 significance and alpha equals 0.01 significance, we need to know our sample size. We had 5 ordered pairs, so n is equal to 5. So we have 2 pairs of critical values. For alpha equals 0.05, the critical value of R is 0.787, and we'd have plus or minus those 2 values, plus or minus 0.878. And then this is for alpha equals 0.05, and for alpha equals 0.01, we have plus or minus 0.959. Ooh, I guess it really depends in this case. Whether our alpha value is 0.05 or 0.01. Because remember how this works. We're taking our test statistic R and we're comparing it to these critical values of R. So at alpha equals 0.05, we're looking at this interval from, it's actually from -1 to 1. And we've got -8.78 here and positive 8.78 here. And our R value of -0.939 is over here. So in this case, if alpha equals 0.05, since the absolute value of this number is greater than the absolute value of this number, this critical value of R is in the tails. So that means that R is significantly low, given that the null hypothesis of no correlation is true. Therefore, we have evidence of a correlation. But at an alpha equals 0.01 level, those critical values of R are very high. So we've got -0.959 and positive 0.959. In that case, our test statistic R of -0.939 is actually in between the 2 critical values. So when alpha equals 0.01, there is not sufficient evidence of a correlation. We're saying even though -0.939 is high, it's close to -1. It's not as close as it would have to be for us to be comfortable rejecting the null hypothesis when we have a significance level of 0.01. So is there evidence of a linear correlation? Well, it depends on what alpha is, actually. So let's go back to the problem statement and see if they mention what alpha is. They don't actually give us a value for alpha. So in the absence of more information, I will just say that an R value of -0.939 is close to -1. So I'll assume that we have alpha equals 0.05 and that we have evidence of a correlation. So in the absence of that information, I would use this I would use the alpha equals 0.05, say we have evidence of a correlation. And that means if we've got evidence of a correlation, the best predicted value of Y, or the best predicted value of that crash fatality rate for a year in which there are 475 metric tons of lemon imports, is given by 16.575 plus this constant times 475. So you just plug in your 475 for X over here, and that's going to give you the predicted value of Y. But now, again, you should only use that equation for the regression line if you have evidence of a correlation. And it's actually a little bit ambiguous whether or not we have evidence for a correlation because they haven't told us what our alpha value is. So we are going to assume that alpha is equal to 0.05 and we have evidence of a correlation. This is evidence of a linear correlation between the two variables. In that case, the best predicted value of Y is given by the regression equation. So we've got 16.575 plus negative 0.002, what was that, 241? No, 2641 times X, and X is 475. And we get about 15.3 as our answer. So let's go back to my lab statistics and type that in. So we have 15.6 fatalities per 100,000 in the population. They say if the regression equation is a good model, substitute the value into the equation. If not, regardless of the value of X, the best predicted value is the mean value of Y. Well, we already knew that, but it was not clear what our alpha value was. So that's frustrating. So I guess we are assuming that alpha is less than 0.05. So we'll assume that alpha is equal to 0.01 in this case. Then we do not have evidence of a correlation or of a linear correlation. So then the best predicted value of Y in that case is the mean of the Y values, which we've already computed in Excel. So let's go to Excel and look that up again. So according to our output in Excel, the sample mean for the Y values is 15.6. So we would use 15.6 if there was no evidence of a correlation. So there are actually two correct answers here, given the fact that they didn't give us our alpha value. If alpha was 0.05, we would have evidence of a linear correlation. So the best predicted value of Y for X equals 475 is 15.3. If alpha is equal to 0.01, then we don't have evidence of a linear correlation. Then we shouldn't use this line for anything. And the best predicted value of Y is just the mean value of Y, which happens to be 15.6. So they didn't like this answer. So I guess we must be in this case where we're assuming we don't have evidence of a correlation. In that case, the best predicted value of Y when X is equal to 475 is 15.6. Actually, I just noticed that I typed 15.6 last time when my answer was 15.3. So 15.6 actually doesn't work. That is the answer we would type in if we had no evidence of a linear correlation. If we do have evidence of a linear correlation, so that's alpha equals 0.05, then it should be 15.3. I don't know how I got that backwards. Okay, somehow my subconscious mind wanted to try this and instead typed this rather than this. Very strange. Okay, so I guess we are assuming that alpha equals 0.05. So we have evidence of a correlation. And then the question says, is the prediction worthwhile? So let's think about it. If we have x equals 475 metric tons, that is in the range of y values, or excuse me, the range of x values for our particular set of 5x values. So I'd say, okay, it's not too far out. We're not extrapolating too much. So that's a good thing. The sample size is pretty small though. So the question says, is the prediction worthwhile? It says, here are your options. It says, since the sample size is small, the prediction is not appropriate. No, I don't think that that's an issue. Since we have evidence of a linear correlation, even with 5 values, maybe the prediction is appropriate. And then B says, since common sense suggests there should not be much of a relationship between the two variables, the prediction does not make much sense. Okay, that's fair. That might be our answer. C says, since there appears to be an outlier, the prediction is not appropriate. And D says, since all of the requirements for finding the equation of a regression line are met, the prediction is worthwhile. Since we're able to meet the requirements for finding the equation of a regression line, they're saying, since that's true, the prediction is worthwhile. I don't think that that would ever make the prediction worthwhile. Just because you can find a regression line doesn't mean it's useful. So D is not the correct answer. Now let's look at our scatter plot to see if there are any outliers. Let's see if C could be the correct answer. There are most certainly no outliers here. Those 5 points are all very close to this line. So there's no issue with outliers. So that's not it. The fact that the sample size is small doesn't imply that the prediction is not appropriate, since we have evidence of a correlation at the alpha equals 0.05 level. So I think B is the appropriate answer. Since common sense suggests there should not be much of a relationship between the two variables, the prediction does not make much sense. So yeah, even though we're able to use the lemon imports to predict crash fatality rates, maybe we shouldn't do that.